What if compromising GitHub and getting access to millions of private customer repositories needed nothing more than a standard get push command with a carefully crafted payload? So this is exactly what the recent GitHub remote code execution vulnerability allowed, and this is what we're going to be discussing today. So hi all, this is Mohammed Abul Khair from AppSec Untangled, and today is going to be part of our lessons learned series. This is where we take real-world vulnerability, dive deep into it to understand not just how the vulnerability works and how the exploit works, but to get some lessons learned out of it that we can apply as we're helping teams build more secure applications. So today we're going to get to the GitHub remote code execution vulnerability, as I mentioned, understand how it works, the underlying root causes and patterns that allow this to be possible, and what we can learn from it as we're building similar software. So let's get to the details. Okay, so this is the write-up. So let's start going through it. So like I mentioned, the payload for this started with this get push command, and to understand how this payload works, we need to get into the basically the design or the architecture of how get handles that kind of input and stores it. So the first thing we need to know is that we have this storage nodes. We have like a storage node fleet. That this is actually where the files of the repositories and everything that customers push to GitHub is being stored. And the impact of the vulnerability allowed compromising, so getting remote code execution on some of these nodes, which in turn allowed access to other customers' private repos. So that was basically the impact of this one. So let's also get to more details about how this works. So this is what happens when you run a get push command and send it to GitHub. So obviously you start by connecting to the GitHub server through maybe an SSH session. This starts by going to this proxy BabelD. So this is just like the first part of GitHub that accepts the connection. And this gets the details. So this includes the push command, your credentials, and so on. So like everything, the options that you included in the command. And this then sends these things to another service, get auth. So this is where the authentication and the authorization is happening. This is where, first of all, let's say you're connecting through SSH, make sure that you are like verify that this is a valid credential. So you do have access to GitHub itself. And then also it verifies that your user has right access to that repo that you want to push to. So this is where the authentication and authorization is happening. Now, after that is done, if you are properly authenticated and authorized, this builds a header called xstat and passes it to the next service. And this is what's going to be actually running on the storage nodes we saw here. So these storage nodes. So everything running on these storage nodes doesn't perform authentication authorization again. It just gets everything it needs. So who you are, the push options, and all of these things. It gets it from this header called xstat. So we build this header, we put everything we need for the execution on it, and this fully trusts the xstat header, which is built after we complete authentication and authorization. So this is how get push works. And to get into more details, we can look at how this works. So basically, we have this xstat header, and this has basically a list of semicolon delimited options. So think about all of the options. If you go to basically the documentation of get push, so anything you add here will be added. Specifically, we have something called get push options as well, which was where the payload of this vulnerability resides. So all of these things are added as semicolon delimited values here, key value list, and is sent back to this service running on the storage nodes. So we do that here. And obviously, just to give you some examples of like this push option. So this is what you send through this -o or the minus push option thing. So this is an extra thing that you typically would be sending to the GitHub server or GitLab or whatever you're sending. So just to share some examples, this in the case of GitLab can be used for changing the behavior. So like you have push options like CI skip, CI input. Then we have things like merge request and so on. So these are just like options for the Get server to act upon. So in this case, we also take these things and put them into the payload or in the xstat header, to be more specific. And the way that this vulnerability worked was all based on the fact that we are using this semicolon delimiter. So all of the options were stacked and semicolons in between. So what the security researchers did here, or the way that they were able to bypass that, is that they gave push options. So again, this -o or minus push option option itself, they added to it this value, okay, as a whole. And as you can see, this value has a semicolon inside it. So when the header was built, it looked like this. From like the proxy side, this looks like, okay, so we have 1, 2, 3 options added. But when this reaches the storage node and the service running on it, now this semicolon will cause these two things to be basically interpreted to be two different things. So now we will have this feature, this option injected. So this is a form of an injection vulnerability. We're very similar to command injection, but we're not injecting a command, we're injecting an option. So we can call it option injection if you want. So we add this, and as you can see, maybe we have this default thing set to true, like for example, reject large blobs. So you can bypass that by putting this payload here, which adds a semicolon and then blob rejection enabled false. So now, because this comes after this one, this is going to bypass it. And now we are changing the behavior that's running on the service. We have bypassed one of the options that's going to be read and is going to manipulate how the service behaves. So this is the gist of how this works. All what you needed is a push option with a semicolon in it, and then you can put whatever option you need. Now, obviously, to be able to move from there to remote code execution, you needed to look for options that allow you to do that. And the thing that the security researcher targeted here was something called a pre-receive hook. So this is something that a script that runs always on your get push to verify limits and stuff like that, as far as I remember. Doesn't really matter, but the point is this runs. And what they were able to find is that if you change, so we saw how to change this one option here, large blob rejection enabled. So what they did is they found that if they changed these three options, so Rails env, custom hooks dir, so this is the directory where this script is, as far as I remember, and then the repo pre-receive hooks, you could actually do just like changing the base directory and maybe using some path transversor payloads. The actual payload wasn't shared in the write-up. But the point is, by changing these three options, you were able to point it to a script that you are introducing and hence run whatever code. So you can do like a reverse shell, you can expose like files, you can do whatever you want. You can run whatever command you want. So you just needed to include a script and use these three options to point to your script rather than the default one that runs here, which is obviously not part of your own code. So this is how this worked. And the other part they also want to do, this worked primarily on GitHub Enterprise server. But what they found is that even like non-enterprise customers can abuse the same vulnerability by changing another option called user operator mode. So again, by changing this to true, this would behave the same way as it would for an enterprise customer. And hence, again, we change the same values and you get remote code execution. So this is basically how this worked. It's all about this injection. You are just adding this semicolon into the push option, which changes the options, hence changes the behavior, and you can do different things. One of them is point to a script to change like the path of the script that's going to be run to one that you own, and hence get remote code execution. So this is in summary how this works. Now, if we go to GitHub's fix, so this is GitHub's own post about it. So if you go down, what they did obviously was making sure that the values are proper. So get options are properly sanitized. So they added input validation. And this can simply be mitigated by not allowing semicolons or maybe even something tighter when in terms of input validation. Because if you think about get push options, like it really depends on the server. So the server usually already knows the list of options that it accepts and acts upon. So you can just put a list of allowed values and not accept anything else, which wouldn't allow the values that had the semicolons and hence make this not possible. So this was a very simple fix for this. Besides that, they mentioned also that they did some other defense and depth stuff. So they found that some of the software running on the storage nodes didn't really need to be there. So they like they basically removed it. I think it wasn't there, but then they applied a new update which pushed it without them noticing, and then they removed that extra thing. So this is how GitHub fixed this one. Uh, and this takes us to the next thing which I wanted to discuss, which is the lesson learned. How, when we are building our applications, we make sure we are not vulnerable or not affected by similar vulnerabilities. So the first obvious lesson here, obviously, is input validation. So we saw that this could be very easily mitigated by not allowing semicolons in the input. And this is a good practice. Like this protects against a whole list of injection vulnerabilities. So things like SQL injection, command injection, XSS, all of these things that depend on user input ending up in a dangerous function or a dangerous thing and changing the behavior, be it an SQL query or a command, or in our case, an option. Just having tight input validation for any kind of user input you're getting. So it could be a list of allowed values, like I said, or it could be a regular expression of with a specific pattern. Let's say if it is like expected to be an ID or a UUID, or even just a list of allowed characters that doesn't allow dangerous characters, because most of the injection attacks need some kind of dangerous character. For XSS, it's maybe greater than or less than. For SQL injection, sometimes it's semicolon or like dashes. Command injection semicolons as well. So the point is dangerous special characters that don't need to be in the input, if they are not allowed, this mitigates against list of or many of the injection attacks. So this is the first thing. And the other thing I would add here is push options. In this case, is a very specific type of option, because it is kind of a nested option. It is an option within an option. You can you have the push options or the get push command options, and then you have push options inside it. So you can add inside this multiple options as well. So be sure that when you have nested input, so we have input, let's say a list of user inputs, and one of these inputs has a list of other options. Make sure your input validation applies to all of these. And this is the first thing that we need to be careful with. It's very good for your security hygiene. It protects against a lot of different types of attacks and provides a very good layer to start with. Now, the other thing I want to mention besides input validation is the fact that this kind of thing, if you think about it and try to ask the question, would a security scanner, so SAST, DAST, or whatever, have been able to catch this one? And I would argue that most likely no. And the reason is what like scanners do, they look for known patterns, known dangerous things, and so on. In this case, if you think about it, how the exploit worked, where you like had this proxy build the header, and then push it to another service. This is not one of the known patterns. So although this is an injection vulnerability, it wouldn't have been picked up, at least by the default out-of-the-box rules. And also, like the input coming from a header, usually this is not picked up by the through the default behavior of these tools. So this is also important to notice and understand that tools like security scanners, SAST, DAST, and so on can help you with specific things, but other things are not covered by them. And that's why tools by themselves are not enough. You need to rely on other things like threat modeling, like when you are working on a design like this one, or code review as well. So we want to make sure that when such code is being added, this is where you would usually spot things like missing input validation and so on. So it is a good reminder that tools are useful, but not sufficient. You need to have threat modeling, code review, and maybe like even use AI to review such specific use cases or specific patterns in your code, because most security tools don't catch it by just going through the default configuration. Okay. The other thing, or the third thing that we can learn from this one as well, is the importance of following the basics of security. And in this case, I would mention least privilege principle. So in the fix that GitHub applied, they mentioned that this basically storage node had access to things that it didn't need to have access to, which allowed this RCE to be possible. So again, make sure when you have similar applications or different or similar patterns that such nodes or such components of your application only has access to the permissions it needs, the credentials it needs. If you're giving it credentials, scope down the permissions of the roles or principals assigned to these credentials to make sure that even if a vulnerability is there, you limit the impact of that vulnerability. So that's the third thing I wanted to mention. Now, the last thing, and probably this is going to be an interesting one, which is when we are talking about tenant isolation, because in this case, the main impact here was broken tenant isolation. By that, I mean that one customer of GitHub can access the data of another customer of GitHub. So you're breaking this GitHub as a multi-tenant, one tenant or one customer can access other customers' data. And this is one of the most serious things if you're building like a SaaS or any kind of application that has multiple customers, because tenant isolation is usually a core security requirement. And the thing I would mention here is obviously when you are designing the application in the code itself, in the application itself, you should always have protection against or like cross-tenant access. So in this case, if we go back here, this get auth service was doing that. This was happening in the code. But the thing to notice is, again, this sometimes is broken. So in this case, this vulnerability, although we are checking that in the code, this injection vulnerability allowed us to bypass that by just running basically after the authorization happens, we actually break out and we are able to execute code on the storage node itself in this case. And this, again, allowed us to bypass this tenant isolation. And the thing I want to mention here, and I want to discuss this generally and specifically for GitHub, which is that sometimes it's a good idea to not fully rely or not only rely on the application level tenant isolation. You want to sometimes do that on the platform level. So, for example, in this case, what if the storage node only had access to this customer's data? So this customer's repositories or files or whatever. So if it had access to one customer's files, this would mean that even if you get remote execution, you wouldn't have access to that. Now, let's discuss that generally and for GitHub. So generally, obviously, if you're not GitHub, you would have some sort of node. Let's take another example. Let's say you have some worker nodes, you have an application, and let's say you want to generate some PDFs. So you have some worker nodes that are being spun up. that reads some information from the database, creates a PDF files, adds it to a bucket, and then users are able to download it from there. So if you want to add tenant isolation, first of all, in the application layer, obviously, like only customers can. So if a customer can submit a job, it should belong to, let's say, a project or a resource that is within that customer's tenant. So that's the first thing. That's the application level protection. But you can also do a platform level protection here by when you are spinning up these worker nodes, you would give them database roles that only has access to the rows that belong to that customer ID. So not the full table, just if this is being done for customer one, then you will give it a role that only has access to the rows that belong to customer one. And similarly, like in the bucket that it needs to write to, it will only be able to write to a specific prefix in the bucket or a specific directory in the bucket that belongs to that customer. So we isolate between customers' files, between a customer rows, so that even if that worker node, let's say if it is using some sort of command to do the PDF generation, and this command has, and like the script has command injection, or if it's using, let's say, a specific library that has a known vulnerability that allows remote code execution. So even if the attacker has full access to that worker node that is reading from the database and writing to the bucket, the worker node itself will not have access to the database or the bucket except for the customer this was created for. So this would not allow this attacker gain access to other customers' data. So this would limit the impact of the remote code execution. Now, let's discuss that in the scope of GitHub, because I think there is also something to learn here. So, like I said, if you look at this as a security engineer, you first think, okay, let's make these storage nodes isolated. So, one, like each customer will have their own like storage node or list of storage nodes and so on. Now, this is very okay as a security engineer to start thinking this way. But obviously, once you take that and go back to the engineering team, to the application architects, you would usually find that there are other considerations, other trade offs that you need to think about. So, for example, in the case of GitHub, GitHub obviously is one of the biggest platforms, and being able to handle the scale of like the number of files created and the number of like customers and so on is huge. So it has a lot of considerations when it built this storage node, and that's why for me, when I had this idea, can we have these storage nodes isolated, I started reading more about the design, and I found obviously there are two main things that when GitHub was designing this storage node, they had to optimize for. So first of all, they had to do storage optimization and hence cost optimization. So the number of customers, the number of people using GitHub, the number of repositories created, the number of files is huge. And if they just took the naive approach of taking every repo and every file and every revision of that file and storing it separately, the storage that they need to handle is going to be huge, going to be very expensive, and also performance may be impacted. So they had to do a lot of optimizations. They had to do things like, we want to do bin packing. We want to make sure that, let's say, if you have very small repos and one really big repo, we want to pack these things into storage nodes so that we can utilize the storage of these nodes in the best way. So that's one thing. The other thing they also had to do is fork deduplication. So if you go here, this is one of the older blog posts on GitHub. They mentioned that, like, for example, some repos would have tens of thousands of forks. And if they just kept copying these files in all of the places, it's not going to be possible. So they decided to do something called, I think, a fork network, which basically meant that if you go and fork one of the popular GitHub repos, the files are not duplicated. You would have a shallow copy of that. So you would have like multiple pointers, but the storage is only happening once. As long as the file is not modified, all of the forks are going to share this one file. So that's one thing that they needed to do, and it wasn't really manageable unless they did it. They needed to have deduplication between different things. And if we go back to the security improvement we had in mind about isolating, obviously this meant that multiple customers already could have this as if, let's say, we have a public repo and multiple customers fork it into private repos. It's still going to be the same storage. So that's one thing that we need to know. So this was really important for storage optimization. Okay, so that's what was one thing. The other thing also was resilience. So if we go to another blog post, they mentioned thing, and if you have heard about the CAP theorem, where you have there are three things: consistency, availability, and partition tolerance, and you always have to take a trade-off with just two of these things. So they mentioned they will have this basically design where each storage will have or like each rep will have three replicas, and they are going to be prioritizing consistency between the replicas and partition tolerance, where it can work even if some of the replicas are down, over availability. So if like sometimes the nodes are not working or whatever, it's going to be like the decision is going to be to just fail the push in this case. And obviously, if you think about adding isolation and just making sure that each node only has one organization or one customer's data, this would add too much complexity over that, which is already like if you go down and I invite you to read this, you'll find a lot of like details about how this was built and how the replication is happening and how nodes interact with each other and so on. Now, I don't want to get to all of these details, but what I want to mention is as a security engineer, it's really important to understand like what makes things more secure. But it's also really important to understand the decisions that the engineering team and the software architects are taking and the motivations behind it, so that when you are suggesting something, you understand how this impacts it. Because it is very easy to go and tell GitHub's team or engineering team that, okay, just split these storage nodes into like just per customer. But obviously, if you do that, you lose a lot of the storage optimization, you lose a lot of the resilience, and all of these things that GitHub was optimizing over the years. So, as a security engineer, my point is you need to understand and speak the language of engineering teams and software architects, so that you, when you come with a suggestion, you have the full picture. So in this case, if you go and suggest something like this, you need to understand that this is a trade-off. And what I would say is sometimes like the most secure option is not the best option. This is not to say that security is not important, obviously, but this is to say that you always need to think about the trade-off and take the right decision. GitHub as a service may not be able to run without these cost optimizations and these resilience factors, and just moving to isolated nodes would break that, for example. So this is something that needs to be taken into consideration. And in these situations, your job as a security engineer is to be able to put the right context in this, understand the risk that we are taking, because sometimes the right decision is to accept a risk, but obviously you cannot really do that uh, with like the right context unless you understand the risk. So in this case, the risk is that we do have a protection against tenant isolation or like breaking tenant isolation in the application, but now we're missing a security in-depth thing in the platform. And the trade-off here is that this is going to be better for cost optimization and for resilience. So now you can record that as take an informed decision and record that as an accepted risk with clear justification why you are taking it. So this was just like a tangent, but I wanted to go through through that anyhow, because it's really like important, in my opinion, for security engineers to be able to speak the same language in terms of like software architecture and code, and be able to understand these decisions, and talk to the teams, understand their motivations, and like put everything in context to take the right decisions. This is an important thing for an application security engineer to be able to do their job and achieve the goal of building better and more secure applications and being able to take informed decisions. Now, leaving that tangent, going back to like the lesson learned, again, it is, if you're not GitHub and you don't have that scale problem, it is always recommended to think about security in-depth tenant isolation strategies, how you limit the access of each node. If you have a worker node or a storage node or whatever, try to limit these nodes and make them isolated to only have access to the things that they need for whatever job they are doing. So this is another lesson learned. So I think this is more or less the things that I had in mind when we went through this. So to recap, we had this remote code execution vulnerability. The cause of it was an injection through just adding a semicolon in the push option. And like I mentioned, I think the main things to take out here is the importance of input validation, a very simple but powerful security control. The other thing is use tools, but don't fully rely on them. Use your own code review and threat modeling processes to catch similar issues. The other thing as well is apply basics, least privilege, limit the credentials and the permissions of these credentials on all components in your application. And lastly, try to have security in-depth controls on the platform level whenever that's possible as well. So I think that's all what I wanted to go through today. So thank you all for watching. I hope you found this useful, and I'll see you in the next one. Have a great day.